Hello, good morning, good afternoon. This is Kubernetes SIG API Machinery bi-weekly meeting. Today is September 7th. Can you believe we are in September of 2022? Time is flying and the year is flying by. So I don't know, carpe diem, seize your days. So thank you for everybody that was able to join. We have 3 topics today in the agenda, and let's get to them right away. The first one is one that we postponed for last meeting. We wanted Daniel to be able to make it. Daniel is here. Shyam, I see you there, right? Okay, very good. So why don't you pick it up?
Hey, can you guys hear me?
Yes, we can. Yes,
okay.
Yes, we can hear you.
Thanks for confirming. Yeah, so we spoke about this on June 15th, and essentially I was talking about if we should consider making some options of gzip configurable through some combination of client and server-side settings. We didn't finalize on that yet. So I think the main feedback was Daniel and David wanted to get some findings documented and like review like the test methodology, and so we can actually go through some of the results now. I just put a link in the chat for the doc where I try to summarize the findings. I think it's shareable, so I hope folks can open that. Okay. Yeah. So I'm not sure how we typically do these since it's a doc. Maybe I can given this link, I can have folks review offline, and here maybe I can go through some of the high level points if you prefer that.
Can we add a link to the agenda notes so that everybody has this for posterity?
I will add it. I will take care.
Okay. Cool.
Yeah. So the background, I'll let you paste that.
Do you want to maybe just give us like a summary and then we can ask questions?
Yeah. I'll do that, Daniel. Yeah. So essentially, like today, the way gzip works is we have a feature kit that's always turned on for API response compression. So it's this from 116. This is the default, and on top of that, the client has to specify the gzip as an accept encoding header. Only then the server tries to compress. And just a note here is we disable that for local controllers like scheduler, controller manager, and stuff. Clayton did this a while ago to save on the CPU cycles and stuff. And this is also only applicable to resource type APIs. So all the streaming type calls like logs, proxy port 4, they don't get gzip compressed today. This is my reading of the code. If at any point I'm wrong, please correct me. And yeah, the final thing is the response size has to be at least 128 KB before for compression to kick in. So this means it's mostly kicking in for list calls only today. So this discussion.
I see it says initial response. What exactly is initial there?
Yeah, I tried clarifying that. So the thing is, for a lot of requests, you only have the chance to decide whether to gzip compress or not at the start, because once you send the client that we are gzipping, then you have to respect that. Or if you're not gzipping, you have to respect that throughout, because for
yes,
some
I
calls,
see those words. They're not answering my question in sort of semantic server terms. What part of the response is initial?
So it's the initial block of response. So let's say there's a watch call. So whatever the initial block of response that you send, there will be other subsequent parts of the response which may come in later. But I think
what Mike is asking is how does one segment like what decides where to cut off the initial chunk?
Right.
Is it like
as someone who looks at, for example,
the
right?
first watch event or what?
Right. Where do I see in the server code this boundary?
Yes. So I put a link there actually. Maybe if you can quickly open the Federico. Yeah, it is. I'm just trying to recollect it myself, but Sorry, I think that is the wrong link. It's somewhere down below, but essentially I think it is, my understanding is it's whatever response is sent to the writer. The initial, so for most calls, it is all of the response. For things like if you're listing something, it's everything together which you send it down to the IO writer. But for other calls where you don't already have all the
Okay, so the answer is whatever happens to be. So after we have done whatever we're going to do, and we're about to call the write function on the thing that is actually going to emit the bytes, it is the size of the first thing that is passed to this write function.
exactly.
Which is kind of a random way of doing it, but okay.
Yeah. Yeah. So anyway, so I think it should be there somewhere in this file, that a bunch of that code.
Yeah,
but
if you just search for the I don't think it's super important to continue on.
Yeah. So if you go back to the doc, yeah, so that's the state, and also we hardcode the gzip compression value to the gzip compression level to 4. It allows 1 to 9, or you can turn it off altogether, or 1 to 9 is like fastest compression to highest, like most compression. And our default in Kubernetes today is 4, right? So what I found through these experiments, and I think there's a parallel set of experiments that was also run by Maciek from SIG Scalability. We actually came to very similar numbers there. And what is the impact of this gzip compression on these responses, right? So I created a benchmark here, right? I explained the test methodology. If you scroll down below, essentially, yeah, like I took like a big box for the API server and a big box for the HCD, so that between API server and HCD, there is no network latency and those kind of restrictions. And then for client, there are 2 cases. I take a small client, so essentially a client is nothing but I created a program. The code also for that is linked in. It's just created a Go program, which basically creates so a given throughput of requests spread across like n clients. You just round robin and make clients, but all of them, it's a Go program that's running on the on this client. And the VM for that is like 2 cases. I've taken 2 cases. One is the small VM and one is a big VM. But in either cases, API server HCD, they are on like really big instances. So there is no CPU shortage, there's no network shortage. And we can see that from metrics too, subsequently. And yeah, if you scroll down to it, so I also linked in, if you just scroll above once, Federico, there was a link for, I just created a small tool and push the code to GitHub so that this benchmark others can also run. And we can, it's just a simple 2-3 Go files that just create objects and list objects. And the objects I tried was with config maps, but I'll also talk about the other object types. So if you go back to the doc again, yeah, so there are a bunch of test parameters which we can tweak, like the sizes of the API server, HCD, and the client, right? And the list throughput, number of clients used, the size, the actual volume of the response size. And there are 2 other parameters which I'll talk about subsequently. One is the entropy of the objects, which decides actually how much does gzip compress, right? So some objects, as it turns out, are much more compressible than others. For example, things like pods and nodes, right? They have a lot of repeating substrings, so gzip can do a lot compressing. But things like config maps and secrets, where you typically hold a base 64 blob of data, it's too random and there isn't much you can actually compress. So the most of the wins you actually get there is basically from base 60, like Huffman encoding converts base 64. So it converts every byte to actually 6 bits because it's base 64. So you get 3/4 reduction just by doing Huffman encoding. And then the final thing is the gzip compression level. So one is you can disable it altogether, or you can also change the levels. Last time I was speaking about disabling it altogether, but this time I also want to bring up the level 1, which is the fastest compression, and yeah, and show like how much it is offering, right? So if you keep scrolling down, at any moment, please pause me if you have any questions with any of these. So yeah, here I gave specs of the instances on which I ran the on which I ran the tests, along with like the client's network bandwidth is one important factor here. For the server and the API server and etcd, they're big instances like I mentioned earlier. And yeah, I created a list called throughput of one QPS, right? And each list call returns roughly 420 MB of response size, like 420 MB of like the uncompressed response size based on the number of objects. I created 10,000 config maps, each around like 42 KB. Right. And yeah, and then I compare the metrics here, right? So if you scroll down further, and these are the metrics I've observed. Let me know if there's any additional metric we should also look at. This was based on discussion with few folks last time. So one is the network bandwidth usage between client and the API server, and also API server and etcd. Just for API server etcd, there is no gzip compression for that part, but just for posterity to make sure that my test cases are actually making equal number of requests. And the other important things is CPU memory usage on, most importantly, the API server, and the etcd and client too. And the final is the list request latency. So this one is the most trickiest one, because this takes into both the compression time as well as the time to send the response. And depending on which beat switch, this can go up or go down in certain scenarios. But what I have actually observed through these tests is, even for really small clients, reducing, if not turning gzip, reducing gzip level 4 to 1 still reduces the list latency, because the gains from the gzip is actually the gains from gzip and network, it doesn't actually offset the CPU spent on the requests. So
can I ask a few questions? The table on our screen, that is comparing level 4 to level 0, or is it comparing?
This is 0 to 4. Okay. There's also subsequently there's a 1 to 4 comparison. So
additionally, I've got an additional question. Above we scrolled past something that said you tried this on a small client where it didn't have that much incoming bandwidth. I'm actually concerned about the opposite scenario where API server doesn't have enough outgoing bandwidth. Did you try that scenario?
Yes. No, sorry, hold on. So you mean API server is bandwidth restricted? And
I mean, it's got a high limit, but there's lots of clients.
Yeah. Yes, I think this. Someone brought this up to me, even like within my team earlier. I think the problem I had there was I needed to run a test on an instance where CPU is high, but network is low. And for most VMs that are like commodity hardware and stuff, most VMs that are available, at least on AWS, and I think that it's kind of pretty similar across providers to have seen, is the network is usually more. So it's hard to get a box where you give more CPU but constant. Yeah.
Nevertheless, you can have so many clients that the outgoing network bandwidth is saturated from API server.
Yeah. So one thing I observed there, Daniel, was it is reaching CPU. So I'll show subsequently through metrics, I'll show you, but it is reaching higher. It is using CPU faster than it is exhausting network bandwidth. So before you actually are able to saturate the network throughput, the CPU usage grows really high. So I can show that here, but okay, can you start from the top of the metrics, Federico? Yeah, so request latency with gzip, without gzip. These are the average and P99 values. And I'm pretty sure at this point that these are actually pretty accurate for such similar setup, because there are at least 2 different experiments from other independent people who actually came to the same number. I have linked that subsequently, the Machek's one, and there was another one a while ago done by someone. But this is these are like some sample latencies and this is client side. I think Daniel had a good point last time that we should measure client side latency. I was looking at server side latency metrics. I wasn't completely sure if that was to the last byte of response being sent. So this is from my Go client I've written. So I see someone, David, you raised a hand, or
yeah, I had looked down. You said that other experiments have been run, and they also show about, does that say 20 megabytes per second? Only 20 through the standard golang gzip on a benchmark.
Yeah. So one was benchmark, but these are more end-to-end tests. So me and Maciek, both of us did end-to-end tests, but that's right. Yeah, so somewhere around 20 to 25 MB per second is the Go standard gzip library.
Okay.
And yeah, so one thing we can talk about it later is one thing which was surprising is like, if there's so much CPU available, why is it limited to 20 Mbps, 20 MB per second? Why can't it happen faster, right? And the problem is I also inspected the Go's gzip default implementation. That library, it is single threaded. So it does not actually parallelize blocks of the rest. Like it does not in parallel compress blocks of the response. I think there are some non-standard implementations of that written by some authors to, I think it's called pgzip or something like that, which you can actually parallelize compressing the response. So the thing is, no matter how much CPU you throw at it, it's still one single coroutine that is just like taking these and compressing block by block and like flushing it out to the underlying IO writer. That's how it's working today.
Okay.
So yeah. So I mean, if you actually have a lot of lists in parallel, it's still pretty good because all those coroutines are compressing in parallel. But if there's a single request, you are not making the most out of the CPU there. So yeah, can you keep going down? So yeah, so P99 latencies. The left side is with gzip, right side is without gzip. But I think we already saw the numbers there. And you can see the HCD, the orange metric is the HCD latency, and there you can see it's with and without gzip, it's very similar, and that is how it should be because there's no gzip involved there. And yeah, the CPU memory usage is the interesting part. So CPU, as you can see, drops, right? If you turn off gzip, it was a pretty steep drop actually, somewhere from 45% to like 10%, about like 4 to 5 times. And memory also dropped. So the memory dropped is an interesting fact, and I dove deep into it. I'll explain soon why that is happening. So yeah, if you go down below, so the memory is actually an indirect effect of how many requests are held in memory in parallel. If each request becomes slower, right, the number of requests at any given point that has to be stored is higher, and that is actually very close. The latency is roughly 5 times, right? And memory also falls 5 times because it's at a fixed throughput, you're having less requests in memory.
So I don't want to interrupt, but I'm beginning to get worried about time. So
sorry, maybe I can go faster. Sorry, Daniel. Maybe over explaining some things. Yep. And the other part is network bandwidth, right? So the red line is the interesting one. That's the API server. That's the traffic sent to the client. The red, orange and green lines is basically between API server and HCD, and that remains pretty same. And you can see for the config map objects, the network bandwidth increased by about, I think, 40 to 50%. But again, this is config maps. This will be different for other objects, so I don't want to over-index on this. But I think the important takeaway is...
But it would be worse for other objects, right? Because config maps are one of the less compressing ones.
Yes,
yeah.
yes.
Okay.
And actually, if you scroll down below, I gathered data. So I ran some script across like 3,000 clusters in our production. And these are production clusters. And I gathered samples of how much is gzip at various levels, helping various object types. So I think we can skip past the CPU profile. The CPU profile, mainly what I wanted to show is that big block of late compressor is actually taking up a lot of cycles. And for memory, you can see that it's roughly same with and without. Only thing is the overall, it's bulged by a factor. So this is gzip level 1 versus 4. And here also you can see like almost 2x drop in CPU and memory just by going from level 4 to 1.
I actually had a question about this section. It says comparing left and right, but left and right don't appear to be the same things.
Oh, it's within the graph. There are two, for within each graph, there are 2 spikes, right?
Oh, okay.
The left side spike is when I had at 4, and then I switched to level 1 and then ran the same test. So that's how the difference is.
So it's opposite the section header. This is comparing level 4 to level 1.
Level 4, yeah. Sorry, yeah, I'll change that. But yeah, and the other interesting part is you can see the network usage almost doesn't change, because for config maximum secrets, I also observed is level 4, level 1 is basically the same compression. For other objects, there is a 2x factor, but for config secrets map, this is the case. If you go down below, this is the most interesting part actually. Yeah, so this is where I collected data from, I think from 3,000 customer production clusters. The font might be a bit small, sorry about that, but these are the distributions for each object type at various gzip levels. How much is the compression factor? This is a distribution of that. So if you basically see the gzip level 1 in the graph right below that is gzip level 4, which are the most interesting ones. So you can see that for pods, level 1 itself on like average, I think average values are noted above, somewhere around 7.5 times is the compression, and level 4 is something around 9.5. So the 1 to 4 is not actually that much of a diff. It is that win is like almost nothing compared to the CPU time that we saw earlier with the latency, right? The latency switch jump is much more. So I think you can just look at these instead of going through all these graphs, you can look at that table. I summarized all the so this is for endpoint slices, services, and so yeah, can you go back to that table real quick, Federico, the one in this section, so people can take a quick look at it. Yep. So ACR is average compression ratio at various gzip levels for various object types. This is the data I collected, because the problem was any test I was running was with synthetic objects, and I didn't want to trust myself that this is actually realistic. So I actually went and sampled this from production. And as you can see, secrets and config maps have some of the lowest compressions. Secrets is like even less.
And in terms of compression time, it's safe to say that level 9 is extremely more CPU intensive than level 1?
Yes. See, it is. So from like 4 to
more
1
than,
itself.
More than twice?
I don't have that number, to be honest, but what I can say is 4 to 1 is a big jump already. Like you saw it went from 15 seconds to 5 seconds or something like that. The P19 earlier. So 4 to 1 itself, there's a lot of CPU saved for not much network gain. So anyway, so that's all. Right.
So thanks a bunch, Shyam, for this. Let me just say what this implies to me and see if everybody else agrees or not. Seems to me that it would be reasonable to just switch our compression from 4 to 1 for everything. And the other thing that seems reasonable is to make it easy to opt out of compression, like a setting in kubeconfig file. I think you can already do it in code, but that it may be inconvenient for some people. I don't think we can completely turn off compression, because some people may be going through small pipes, like distant connections. And like this might be the difference between getting everything to them in 60 seconds or not getting it to them.
Yeah, I think the other question is, who would be making this decision? Is it the admin running the API server? Is it the developer of the client? Is it the user of the client?
By saying it should go in the kubeconfig, I'm saying it's the client or whoever's configuring the client. David, why don't you say what you think?
Yeah, so I'm looking at this and I'm glad I finally have a reason for why we seem to be capping out at 20 megabytes per second. And I think my question is a little bit different. My question is, why would we stick with a poorly performing gzip compressor? The link that you provided was actually to someone else's repo who claims that he has a compressor that I believe it says is compatible with gzip that runs 10 times faster. And that would seem compelling.
So just one thing to clarify is some of these implementations actually parallelize the gzip, right? That may not be a really fair comparison, because when the CPU is exhausted, you're still doing only as much work as you have. Even if you parallelize, let's say if there's enough list throughput in flight, then you won't get much wins by parallelizing. So that benchmark, I'm a bit skeptic about like that. There are in general, but I think you bring up a right point, which is there are various compression algorithms, and even outside of gzip, there's I think ZSH, which is supposed to be at least like 2 times faster for similar compression ratios and stuff. We can consider alternative compression algorithms too. I think the default.
So,
sorry.
One reason to stick with gzip is because then we don't have to change any clients, which would be a large undertaking. But I wasn't saying we shouldn't make further improvements. I was saying like if somebody gave me a change to switch from 4 to 1 tomorrow, like I'd LGTM that. That seems pretty like a pretty clear win. Doesn't mean we shouldn't continue to improve it, but I think that justifies like just making that change right now.
One question I have there, Danny, is do you think it should be a flag instead, or should we just change the default? Because what if someone needs it to be 4 and we'd be backward incompatible?
I mean, the multiples on the like how much more CPU it takes to get how much less network bandwidth, it just doesn't seem like anybody is going to want the other option.
The table that you put together is very convincing. I also would say going to level 1 is an easy win.
Yeah. Only thing is, maybe I can talk with you a little bit offline as well, because if someone for whatever reason they need to keep it at 4 and now they have no way of doing it.
I'm sorry. So do you have anybody in mind? I mean,
yeah, I just don't see it.
It already isn't under the user's control. Why do we want to add control?
So I think okay. So maybe another thing I want to talk about is like a bit futuristic. I think, and this is an idea which Clayton also was entertaining earlier, is we might want to override these gzip values at an object type level, because there's an issue linked at the bottom of this. It's just an idea. You might shoot me down totally, but I just want to mention because
look, we can imagine anything. Do we have uses? Do we have anybody who actually says, I need this?
Because what I was saying is for secrets and config maps, we can technically just turn gzip altogether. We don't have to stay like this one will basically force us to be at 1 everywhere. It helps a lot for pods and nodes is what we've seen. But for secrets, even 1, it barely helps.
I'm the configuration overhead is really extreme. Like it's already extremely hard to configure API server. The bar for adding additional configuration when we can just do something simple and get most of the benefit is just extremely high.
Yeah,
I'd be willing to entertain the proposal non-configurable, that this is disabled for config maps and secrets.
Yeah, I would also be willing to listen to that before a proposal to make it configurable for everything.
Yeah. That's definitely a valid point. We could actually do this.
I wouldn't want to be the guy trying to plumb that. I did have a question about the average compression ratio showing, if I'm understanding it correctly, that we should see like a 50% reduction, maybe a little bit more in throughput outbound from the API server, and your bandwidth usage check appeared to only show about 30% reduction. Is that just because of the types of objects you used?
Yeah, I used config maps, so the difference is lesser because it's in general less entropy, so it doesn't compress much. With pods, it would have been higher. It's still for the instance type I used, it still would have been within bounds.
Can you help me understand how that compares to the table for the object type showing the average compression ratio at 4? I believe the average compression ratio for config maps was 6. And I might be misunderstanding what this means, but I would have thought that meant that I should expect to see 1/6 of the network bandwidth used.
Correct.
Do you have any theory for why we are seeing, instead of 1/6, we're seeing 2/3?
Yeah, so because this is from real production clusters where config maps they may be really small objects, right? And there may be more of metadata and like a spec and those fields compared to objects and stuff, but secrets is more prominent actually. And the tests I used, I basically created a huge blob of data, which is more than 90% of the object is just the base 64 stuff. So
this table says it was collected from a random sample of customer clusters.
Yes.
There's two different things going on. The table is analysis of customer data. The test above was run with generated secrets and config maps.
Right. And so the reason I'm looking at it is because the story from the benchmark, when you look at those graphs, is like, well, you aren't really saving that much data anyway. But when we look at the expected benefit on average customer clusters, we would expect to see this bar on the left, instead of being at like 18, we would expect it to be at 4, which is like right now, this chart makes you look and say, well, why are we doing this at all? But when you see compression take you from 25 gig sent to 4 gig sent, well, then you can say that's why we're doing this.
Right. So yes, can I suggest something?
Oh, also one other thing is this is comparing gzip disabled versus enabled. 4 versus 1 is like a much lesser drop, because that's what that other table showed. And basically, David, you bring up a very good point. This is exactly the reason I collected data from production, because this is the first thing I get is like, is your workload even realistic? So yeah, so just don't consider much that network bandwidth part too seriously. That was mostly for CPU usage and memory usage and latencies and stuff like that, for which
All right. I think Mike was trying to ask a question, so let's let Mike ask the question, and then let's wrap this topic up.
Well, I was proposing to factor the discussion. I think maybe we have a quick decision to just change 4 to 1 now, and come back later with a question about what to do for maybe exceptional treatment of config maps and/or secrets.
Yes.
Or I think if we're going to do something more complicated on the table, we should also consider switching to a faster compression mechanism, which involves changing clients, or I don't know, intelligently like measuring network bandwidth to this client and deciding what level to use automatically based on that. I think there's a lot of options if we're going to do something more complicated, but I think today just turning it down to level 1 should be a big win.
Okay.
That parallel gzip claims that it's still gzip. So
yeah, it's using multiple
that should also be
rotates.
That should also be on the table. Although if it's getting a win by parallelization, I'm not sure that would translate to a win in practice in large clusters, since we're already highly parallel.
Correct. Okay, so I think thanks for this. I'll cut an issue and summarize what we decided, and I can change that level later this way. I think there are basically 4 things. I'll quickly summarize. 4 to 1. The other is we might want to have kubeconfig, a disable compression field in kubeconfig, so clients can disable this from their end. The third one is, I think the flag is not really something we want, but maybe within the server itself intelligently decide level based on the contents of the objects. Yeah, I think those are all for now.
All right, thank you very much.
Thanks.
It was a great presentation of the maybe even more data than necessary, but thank you for being thorough.
Thanks.
All right, Joe.
Hey, so I'll try and be pretty quick. I wanted to start getting ready for 126. We are interested in writing. We have a draft KEP for self for admission control. Previously, we used self for CRD validation. I wanted to quickly gauge the SIG's level of interest to consider a KEP for this in 126, and then also get if it is acceptable, try and convince somebody to be willing to do an early review pass, because I think it's going to, if we try and do this like the week before the deadline, I think it'll be hard to get the reviews done for it. It's a bit larger of a thing. I can, if we have time now, I can go over a couple of the major issues that we're looking at, but that's mostly what I wanted to check with the SIG about.
When we had previously talked about this, I think it was Mo and myself had pointed out that a large number of admission plugins that we were familiar with followed a pattern of let me do a secondary ACL check. So I needed a second authorizer check based on the input. Is that in scope or out of scope for what you're describing here?
I think we want to get into that one. I don't know if we would do it in the first alpha or not. We're trying to figure out all the auxiliary bits of information that we're going to need to cover various use cases.
Are you comfortable making it blocking to get to beta?
Yes.
Okay, because I'm comfortable going through multiple alphas, but I'm looking at the admission plugins we have and what benefit you get from this versus validation, and external ACL check is a really big one. And so getting started with one alpha, sure, but before going to beta, having that capability, this is what we can do, I think is important.
Okay. Yeah, that's good feedback. I will track that. Do we have time for me to go over like one of the largest issues on the API shape? I can try and cover it in 2 or 3 minutes.
The agenda topic that I have is really short.
Okay, great. Yeah, I will try and get this. Fede, if we can switch to just I think the thirds, let's just actually just move through these slides really quick, just the first 4 or 5 slides. So the second one.
There is a hand by.
Oh yeah, go ahead.
Sorry, I just wanted to argue against the secondary ACL check, but I think that's not the most important thing to cover right now. So we can follow up on that later.
Yeah, we can have a side discussion on that as needed. So this is, I mean, for anybody that's not clear what I'm talking about, this hopefully kind of gives you some clarity on just the most basic way to express the idea, which is instead of having a webhook for admission control extensions, you would basically use the same concept, which is you're going to register on which objects you care about for admission control, and then instead of delegating to a webhook, you're just going to write a cell expression saying what you want your check to be. So the next slide, one of the bigger issues that we've been talking about recently on this has to do with the fact that a lot of use cases are focused on policy enforcement. And in many policy cases, and this is an example of that, you need some kind of configuration data. So as a motivating example, say you have like a block list and you want to enforce that like the metadata and like the object's name is not in the block list. This is just a really simple example of using configuration. You could try and embed that list into Cell, but it's super gross and it doesn't scale very well. And if like you want to have a different configuration depending on like what namespace you're in or some other criteria, it gets even worse. So one of the big things we're trying to figure out is how do you handle configuration. On the next slide, I had a really simple way that this is kind of what you see if you actually look at policy enforcement engines. What they do is they split between the policy definition, which I'm showing here on the left, and then the policy application within a cluster. So the policy definition is usually written by like, the owner of the policy framework. They don't know like how you're actually going to apply the policy rules. So this is like a rule for saying that you can only have so many replicas, like there's a max number of replicas that you can set on things. Silly example. And then what you do is then you have to have some configuration somewhere. So policy engines tend to do a split. If we did it this way, if we tried to retain their abstraction, we would have to do something like maybe put some information about what the configuration schema is into the definition on the left, and then maybe we generate a CRD for that, and then people create CRs to conform to that, and then we have all the information we need. This is one way to do it. I have 2 other ways, so I'll look at them really quick. The next one, this one, instead of creating the CRD, you just reference a CRD. So you're not responsible for having like part of the system creating CRDs. You just say like, this is what your configuration is. And you can still type check that against your cell expression if you want to make sure that it's valid configuration. But you're not actually getting like involved in like having the schema information directly in the object. And then the third one, I'm struggling to figure out which of these is the best based on various criteria, would be to like not even have like separate objects. You just like flatten all the information into a single object. And so here instead of having the configuration being in a bunch of objects, you just have a list of configurations, each paired with their match rules. So here I have two. One is like for prod and staging where the limit's 100. The next one's for test where the limit's 3. And so depending on which match you get, determines which configuration you get. If you match multiple configurations, then you would actually just run the expression multiple times with all the config. So this is one where I'm really interested in people's take on like what is viable from an API server perspective. Should we try and get really close to how people want to express it in what we've seen in the past in policy definitions, or does like starting to like generate CRDs and have all this stuff involved get too complicated?
So this is me not fully understanding what you've shown here, but on the next slide, or maybe the next one down, this one. These rules, is the schema for these rules always effectively fixed so that the schema for whatever referenced type you chose would have the same schema over and over?
Yeah, exactly. So here, I mean, you could even maybe infer the schema, right? This one, the configuration has a max replicas field, which is an int. That's literally the only thing you've got. Another configuration might have multiple fields. It would be really complicated, but that's this one. And in this case, you would only ever have one configuration schema for this whole thing. So then each of these rules is just like conforming to that schema in its config section.
Mike?
So is the first two of these, which talk about additional objects, is that the same kind of thing we were talking about earlier, where the checking involves, someone said something like secondary objects?
Yeah, they are additional objects, right? So you've got a bunch of objects flying around, and the CRD could be deleted because it's a separate thing. So there's a lot of complexity that comes from that in 1 and 2. Did that answer your question?
I'm not sure. I guess I was actually just trying to understand the topic that someone brought up. Again, they got into the answers about alpha versus beta. The question was, someone would say something about checking often involves looking at, I forget exactly the term used, secondary objects or something like that.
Secondary ACL check. It's a different technique here. It would be something like a feed data to some sort of function that means check the kube API server authorizer to see if the subject or the client has permissions to do X. And you use it to control fields like controlling subsets of objects. You can imagine someone might want to say control a subset of a finalizer. And this would be how you would do that.
All right, thank you.
Tim?
Yeah, I think an important question that we need to answer for this is to what extent we want a complete solution out of the box, or like kind of how complete we want that solution to be. Because with something like the second option, or really even the like no config option, it would be pretty straightforward to build a controller that accepted any type of API you want and kind of compiled that into a webhook, or not a webhook, a cell admission policy, right?
Yeah, if you look at the last option, FedA option number 3, this aligns really closely with what the API server is going to need to have in memory when it's actually in the admission chain processing requests. So the first two options, if you only gave people this option, they could arguably take a controller and build either of the first two options on top of it.
Now, reading this, I gather the rules and the namespace selectors have a fixed schema, but the config actually looks like it can have any schema it wants. I could put as many fields as I wanted.
Yeah, in this one, very near the top, you actually declare what that schema is. There could be a variant on this where, because all of the data for that schema is contained in this object, you could even try and infer it. But I think there's some corner cases where that gets really messy, like an empty list. So our proposal was that you would at least define it somewhere, even if it's in the same object where you have the instance data.
Mike has a hand.
Right.
Yeah, Mike.
So to answer the question, then I do understand the sort of the virtue of the third, which is if it's, you know, what's really needed and anything else can be layered on top of this, that's great, except I'm concerned that that gets to a performance anti-pattern, right? If you get into the business of requiring frequent updates to large objects, you've hurt yourself.
Yeah, the practical downsides to this one are exactly that, and also that, you know, you could eventually hit the size limit on this. So anybody that was writing those controllers would have to deal with oh, I think I'm getting towards the object size limit. I'm now going to generate 2 of these admission control things and split my match rules across them or something like that. And if you were instead natively implemented one of the first ones, you wouldn't necessarily have to do that. Although you would be keeping like a bunch of, you'd be managing shared informer or some informers in the API server and doing stuff that is more typically considered controller behavior. You'd have to do that in the API server.
Right. But I think that's better than getting into the business.
We do that with CRDs, but it still would be more.
Right. I think that's better than getting in the business of large objects here, both in terms of frequent updates and too large. So then my reaction is, yes, let's think about the sort of the minimal way we can break this up into multiple objects. Oh, the other thought was, who's in charge, right? Who's the author? I guess that gets to the other issue though, right? If you have different people sort of having different roles, that kind of naturally leads to multiple objects, so that RBAC can allow different people to exercise their different roles.
Yeah, that's a really good point. Typically, the developer that builds the policy rules themselves is different than the person that's configuring them to be used in a particular cluster. And I would expect that a lot of cluster administrators might be quite a bit more lenient on who gets to set up some of the settings on maybe their region of a cluster than they would actually like redefining the policy rules.
Yeah, region of the cluster is an important aspect there, right? That would be something like I set up the namespace selector and I let you set up the max replicas. And to do that, you'd want a secondary ACL check as a for instance. Mm-hmm. The one other pattern I've seen for handling this is to actually have an object inside of the namespace that a namespace admin isn't allowed to touch. An example of that would be, say, quota, where in cases where you want configuration per namespace, you can actually create configuration per namespace, keeps the size of the object down, and makes the rules about who can access things in certain namespaces easy to maintain via RBAC.
I like that capability. I'll look into quota and see if we can, because right now I've basically just kind of copied in what webhooks had for matching, but I think we can do better once we introduce this as a separate object.
I have a question.
Oh, go ahead.
Oh no, go ahead.
I was just gonna say that size-wise, I would probably be biased towards having the separate objects because I know the schemas can get very large, and trying to evolve a schema over time is something that I will also be asking about on the KEP. And I think CRDs already have some ways for you to manage that. And I don't know whether you'd have to reinvent them here or not, but that's going to be an area of concern I have.
Yeah, I'm really concerned about that. One of the reasons I like option 2 is you just reference an existing CRD and you basically don't get into that game at all.
So I have a question, which is, do you anticipate ever wanting to do different rules for different users or different groups, or is this just rules about the resource, which everybody has to follow?
That's a really good question. I hadn't thought about per user rules. I can look at that as some of our use cases and see if we can find ways. I expect that almost every dimension where somebody's going to want to be able to, like, you know, drill down to, that they're going to want to over time. So as a sanity check, I think it would be good to see if we can support that.
So specifically, like, I've got in mind the case where I want to limit a certain controller to only writing, say, finalizers on objects and not anything else.
Well, you will have access to the user info in the admission request. So you would already have that in the expression, but you would still have to be like checking every single object. You wouldn't be able to do that at match time. Although I'm not sure that that matters as much anymore, since you're just like, cell's pretty cheap to evaluate.
Yeah, I think it's more that you'd have to build that into this definition that you've got on the screen somehow.
Yeah, and naturally, one way to manage that is via an RBAC check. But I would like the last 5 minutes if I could, Faye.
Yes, this was really helpful. I think I already got what I needed. Thank you.
Thank you, Joe. And yes, David, I was going to give it to you.
Thanks. So one thing that's coming up is that our V1 Beta 2 for priority and fairness begins its deprecation period this release. And per the no perma beta, our choices are V1 Beta 3 or V1. I'd happen to think Mike is here, and so I wanted to talk about it, but I think that we are still talking about changing some functionality that we have around sharing, and so I'm inclined to go V1 Beta 3 as our starting point this release.
I'm afraid I agree. I think we're talking about a big enough change that I think it would be, the honest statement would be beta.
Okay. Well, that was a whole lot easier than I thought. So yeah, I'll talk with Abu and see about getting a PR up to go ahead and start V1 Beta 3 so we don't miss our time.
Thank you.
Okay, so I guess we are good then. Thank you everybody for coming. I wanted to say that we are David and Jeffrey. They are preparing a virtual talk for KubeCon on advanced API machinery topics. One is going to be aggregated API servers, and the other is going to be OpenAPI v3. And then I don't know about the rest of the group. Some people here at Google are planning to go to KubeCon in Detroit, so we may see each other in person. I have to check the dates. We still have potentially a couple of meetings before KubeCon, so we will see each other here yet. Reminder, we still do twice a week back triages. Mike, thank you for coming to join us, and everybody's invited. So that's all for now for today. Thank you for joining. Hope you have a good Wednesday.
Thank you.
Thank you.
Bye-bye.
Bye.